Okay, so here is a basic telescope. Lovely drawing here, all right? And you hopefully are aware that the telescopes before Newton's, the one that Kepler used, had a lens, a convex lens here. And it also had an eyepiece, which is a convex lens. This lens, by the way, is called the objective lens because it's near the object, and then the eyepiece because it's near your eye. That might be obvious. Now, first of all, the eyepiece is not much bigger than your eye because you put your eye right up against it. It doesn't need to be large. The objective lens will be large to collect as much light as possible. A lot of incoming light, because you're usually looking at things in the distant night sky. You would like them to be brighter to be able to see them better. So you want to capture as much of the light coming from them as possible. So if the objective lens were small, not as much light would be captured by it. Other things about this is the objective lens has a long focal length, while the eyepiece has a short focal length. Now we'll talk more about why in a moment, okay? But first we need to figure out, okay, where will when we have two lenses, okay, the first lens has light coming in to it, and it will create an image that the second lens can look at. So every system with multiple lenses, you can say that the image from the first lens is the object of the second lens. The second lens is looking through the first lens just like you would with your eye, okay? So we're looking though at objects that are far away. So DO is very large. Even if you're just using a telescope to look across the yard, in terms of centimeters, that's, it could be, 20 meters is, what is that, 2,000, 2,000 centimeters. That's a lot of centimeters. Okay, so DO, the object length, is very large. When we're looking at faraway stars, DO is extremely large. In fact, we'll say that it's infinite. All right. So if we use the thin lens equation, and you substitute infinity in for DO, obviously, when you take 1 and divide by infinity, that becomes 0. So what does that tell us? The image is going to show up at the focal length of the first lens, okay, or the focal point of the first lens. So we're looking at something that's very far away, so its image is going to show up we want it to show up close to the eyepiece down here. It will come into focus. There would be a small inverted image of whatever it is you were looking at. That was, more or less just a little dot in the sky from very, very far away. All right. Now that image might be, I'm going to put a little optical axis in here. It's going to appear along the optical axis, and it's going to be small. Okay. Now, the image, you might think it's not very useful to have a small image of something that's very, very far away. But remember that you're looking at something that's very large, very far away. So actually, let me change my image to blue here, and I'm going to put in a ray. So there is some tiny angle here. But that angle, if I were to look at this point at the end of the telescope, if I'm assuming my optical axis is pointing at some distant heavenly body, okay, and there's a small angle that the heavenly body takes up in our line of sight. And so that would actually just be a straight line out to where the edge of the object that we're looking at. So it could be the edge of a distant planet, assuming the optical axis is pointed at the center of the planet. That would that ray that I've drawn in would be pointing to the outer edge of it. And it's going to be an extremely small angle that we're looking at, but that same angle will be made with the optical axis within the telescope, right? Now that doesn't seem so useful, but now here's where the power of the telescope comes in. We now have a magnifying glass that is looking at the image from the first lens. And you can see that this angle right in here that is made relative to the eyepiece is a much larger angle, right? So ideally, we want to have as long of a focal length. Oh, there are two triangles in here that matter in terms of the magnification that we're going to see with our telescope. There's this end is where the eyepiece is, and your eye's right behind it. This end is where the objective is. All right, and the further down we can get this image to the eye, the more angular magnification we can get, because you can look at the triangle that I'm making. Not too bad. All right, the image, there's an angle in this triangle that would represent the angle that the object in space takes up when you look at it from far away. And then over here is the image, is the angle that it takes up with your eye as you look at it through the eyepiece. So let's call this theta 1. Theta 1 is essentially the angle you would see if you take the telescope away. And theta 2 is the angle of vision taken up by the image within the telescope when you're looking at it through the telescope. And that can be significantly bigger, right? And it turns out that based on these two triangles, because we're talking about small angles, theta 2, so the angular magnification is basically theta 2 over theta 1. And when we're talking about small angles, that ends up meaning that we can look at the similar triangles here. We can say that in looking at this, the tangent of theta 2, that's approximately equal to the tangent of theta 2 over the tangent of theta 1. And the tangent of theta 2 would be would be the height of the image divided by the focal length of the eyepiece. Okay, because remember we said with a magnifying glass, you would be looking at an image that's essentially just inside of the focal length. Okay, the theta 1, if we look at I should remind you, tangents are opposite over adjacents. Okay, so the opposite side is where the image is, and so the height of the image would be the opposite side, and the adjacent side would be the focal length of the objective lens. All right. Now, because of the reciprocal that we have here, this ends up being the focal length of the objective lens over the focal length of the eyepiece. All right. So it's all about changing the angle of vision, not necessarily, you're not doing a lateral magnification of the object you're looking at. You're doing an angular magnification, and the telescope allows you to create an image that is nearby that we can then use a very powerful magnifier to look at, and we can increase the angle of vision taken up by the object, and therefore it will, when we project it back onto the retina of our eye, it will take up more of the pixels. It'll take up a bigger region on the retina, and therefore you get better resolution of the thing that you're looking at.